JavaScript, and give him a warm welcome.
Well, thank you, Marcus. So yes, my name is RussellKeith-Magee. In my day job, I am a data engineer at Savata. We're a brand intelligence platform. We use Python and data science to deliver consumer insights, predictive analytics. We help our customers improve the impact of their brand marketing. They give me the flexibility to attend conferences like DjangoCon and PyCon, for which I'm very thankful. But I became involved in and I'm known to the Python community through my work on Django. I joined the core team way back in 2006. I'm not as active in the core team as I once was though, and that is at least in part because of the way that the web has changed. Over the last few years, web development has become increasingly JavaScript heavy. 15 years ago, when I started working with Django, you could almost ignore JavaScript. Now, your logic was all server-side, and the client was just navigating through a static series of pages that, okay, may have been generated from dynamic content, but they were static when they were delivered to the user. It is a lot harder to ignore JavaScript these days. Users expect a rich client-side experience, and JavaScript is the only language that's available in the browser, so that means you need to use JavaScript. Note though that I say use JavaScript, not write JavaScript. What I'd like to talk about today is a development in the JavaScript ecosystem that has the potential to reduce the significance of JavaScript as a language and opens up a lot more possibilities for Python and by extension Django. That development is WebAssembly or WASM. To explain what WASM is, we have to dig into how you actually get code to run on your computer in the first place. When code runs on your computer, it is running as machine language, binary instructions specific to one particular CPU and operating system. Those binary instructions aren't easy to write by hand, and so one of the first programming interfaces was assembly language. Assembly language is a human-readable version of machine language. Every machine language construct is exposed directly as an assembly language analog, so assembly source code can be easily assembled into a machine language binary executable. Now, I say human readable. Assembly code isn't that easy to read, or write for that matter, and so developers wrote abstractions. The first level of abstraction comes in the form of compiled languages like C. In a compiled language, you take your source code, you run it through a compiler, and that produces the equivalent assembly language, which can then be converted into machine language to produce an executable. Modern compilers often compile directly to machine language, but internally the same transition is happening. When you send a C program to someone else, what you're passing around isn't C source code. It's source code converted into machine language form so that it can run on the CPU of one particular computer. It doesn't contain any remnants of the original source code. The compiled executable form is tightly bound to a specific CPU architecture and to the libraries provided by a specific operating system. The next level of abstraction is an interpreted language like Python and like JavaScript. When you send a JavaScript program to someone else, what you are sending is the source code. However, at the end of the day, a computer does everything in machine language. The interpreter is a machine language native executable that can read the source code and interpret the machine language consequences of the source code it has been given. The benefit of this approach is that the code you pass around isn't machine dependent. The same JavaScript source code runs the same everywhere because it is the interpreter that's doing the hard part of working out what machine language instructions are needed on this machine to produce the desired effect. Now, let's say we are using JavaScript and we define ourselves an add function. It takes two arguments, it adds them together, and it returns the result. When this is run through your interpreter, the interpreter has to convert it into CPU instructions. But which CPU instructions? If first and second are both integers, then we need to do an integer add operation. If first and second are strings, we need to do a string concatenation. If first and second are different types, then all bets are off. It gets a lot more complicated. That means the interpreter has to be ready to do almost anything because the code will allow it to do almost anything. The price you pay for that flexibility is that your code is a little bit slower. However, because JavaScript is now so important to the end user experience in the browser, the runtime performance of JavaScript engines has seen a lot of performance attention. Once your code starts running, you might find that because of the way the code is being invoked, the arguments are always integers, and the interpreter can exploit that. Once the code is executing, the interpreter can identify patterns of execution. It can see that our add method is only ever being invoked with integers, and therefore develop an optimized interpretation of the add method that will only do integer math. Because of that narrowed scope, the optimized version is faster because it is closer to the bare metal machine language instructions that the computer actually needs to execute. This is effectively the same thing that a compiler is doing on a compiled language, but it is happening at runtime. And for that reason, the process of what the interpreter is doing is called just-in-time compilation, because the conversion to machine language is happening just in time for the code to execute, in contrast to the ahead-of-time compilation in a compiled language. So a just-in-time or jitting interpreter will optimize the code at runtime to make it run faster. The question then becomes, can we game the system? Can we do something to our code that will make it easier for the interpreter to identify possible optimizations? Turns out the answer is yes. For example, in JavaScript, the result of a logical OR with an integer is always an integer. So if we OR an integer with 0, you will get the original integer. So if we OR both of our function's arguments with 0, the interpreter can know that the addition operation must be an integer operation. It doesn't matter what type first and second are, the addition is an integer addition, and the result must also therefore be an integer. This is something that then has a direct interpretation in machine language and is therefore fast. Okay, so that's a neat trick, but why do we care? After all, we have to deface our code pretty badly in order to realize that optimization, so is it really worth it? Well, no, if you're looking at this as a way to speed up your handwritten JavaScript, probably not. But take a look at what we've just been able to do. By doing nothing more than annotating our JavaScript code, we have been able to convince the JavaScript interpreter to give us near direct access to optimized CPU-level integer arithmetic. It's a very roundabout way of expressing it, and the optimization doesn't happen until the code is actually running, but we have used an interpreted language to expose a primitive machine language construct. If we can expose one machine language construct, can we expose all the capabilities of a machine language? A few years back, a team at Mozilla looked at the JavaScript language as a whole to determine if there was a subset of JavaScript code annotations and conventions that you could use to trick a jitting JavaScript interpreter to expose near direct access to the full capabilities of your CPU. And what they came up with is called asm.js. asm.js is 100% legal JavaScript code. It is not pretty JavaScript code. It uses only a subset of everything that's in the full JavaScript spec, and the code is covered with annotations and weird coding conventions like the zero ORs from before. But in combination, those annotations and conventions provide a set of low-level primitives for performing integer and floating point arithmetic, allocating memory, defining and invoking functions, and so on. Capabilities that map directly onto the capabilities of machine language. They have effectively defined a way to expose the machine language capabilities of a CPU using nothing but a platform-independent interpreted language, JavaScript, which means it is effectively a cross-CPU assembly language. But even asm.js can be improved upon. What is delivered by asm.js is still just JavaScript code. Admittedly, it's almost illegible JavaScript code, but it needs to be transmitted in text format, then parsed, then interpreted, then executed, and then jittered. If we know ahead of time that our code will be compatible with that fast JavaScript subset, can we send our code to the browser in a ready-to-use format? And that's what WebAssembly is, or WASM. WebAssembly is a binary format, formalizing the asm.js language subset in a format that can be delivered to the browser in a pre-parsed, pre-hinted for jitting purposes form. That makes it smaller to transmit than asm.js code because it's binary. It is faster to start because you don't have to parse the code, and it's more consistent in operation because you are telling the JIT exactly what operations are legal and where the optimizations are. So that's how we got here. But how do we actually use it? Well, the development story for WASM pretty closely mirrors the story that I've already just gone through telling you about running normal executable binaries. WASM is ultimately a binary format, but unless you belong to the standing in a hammock school of engineering, you are not going to write every WASM code directly. What you want is a human-readable, text-based assembly format that can compile directly to WASM. The toolchain you need to do this is called the WebAssembly Binary Toolkit. This gives you a whole bunch of tools for manipulating, compiling, decompiling WASM code, including an assembly language compiler that lets you write WASM code in a text format called WAT for WebAssembly text. WAT looks like a weird hybrid between Lisp and assembly. It is a core set of primitive operations with a brace syntax to make scoping rules explicit. So here is our integer addition example in WAT. We define a module. Our module contains a function called add. Add takes two parameters, first and second. They are declared as being 32-bit signed integers, i32s, and the function returns a signed 32-bit integer as well, an i32. We then get the body of the method. An executing WASM method is a stack-based machine, virtual machine. So to do our addition, we need to load the values provided as arguments onto our operating stack. We load the argument first. We load the argument second. We now have two arguments on our stack. And we can invoke the integer 32-bit add operation, which pops two values off the stack, does the addition, pushes the result back onto the stack. We're now at the end of the method. The value that is on top of the stack at the completion of execution of the method is considered to be the return value for that method, and so we've just implemented an add. That completes our method definition, so now we can export that function to say we want other modules to be able to see this add function, and that's it. If we save that code as example.wat and we run the compiler called wat to WASM over it, you get example.wasm, which is a 41-byte binary file containing those instructions. To use that WASM file, you do need to write a little bit of JavaScript. We fetch the WASM document, same just using the fetch API in JavaScript from the browser. We use the payload of that document to instantiate a WebAssembly module, and then we can access the exports of that module and invoke them, in this case, the add method. The add method returns an integer. We can do whatever we need to do with that integer. In this case, we're going to set the text content of an element on our web page. Now, to be clear, this isn't some theoretical future thing either. This code, that example code I've just shown you, will work in any browser that has been released in the last 2 years. There are a couple of optimizations you can do if you're using Chrome and Firefox in terms of loading it. That fetch example is only completes its load once the document is entirely loaded. There is an incremental compiler that's part of an evolving JavaScript spec. But this code will work in any browser that's up to 2 years old. Okay, so that's a simple addition example, but integer addition is only going to get you so far. So what else can you do with WASM? Well, WASM is an assembly language. It is primitive, very primitive. The full WASM instruction specification is one relatively terse HTML page, and it only has 5 sections. First, there are numeric instructions, add, subtract, multiply, divide, booleans like and or, function operations like square root, ceiling and floor, max and min, and comparison operators like equality, less than, greater than. These can be invoked on integers and floats in 32 and 64-bit ranges, signed and unsigned. Then there are variable instructions, operations to get and set variables in your local scope. There's also a thing called T, which lets you set a variable and keep it on the stack at the same time. Next, there are control instructions, mechanisms to do branch control, looping, invocation of other functions, returning a value from a function. There are memory instructions. There are mechanisms to allocate a block of memory for the WASM interpreter to use, to load and store values in that memory. Memory is implemented as an array of bytes. It's just a great big array that can be grown, can't be shrunk, but you can point-to-point locations in that memory and do things with that content of memory. And lastly, there are parametric instructions, which exist to let you discard values that exist on the stack. These instructions are then wrapped up into a module. A module obviously includes function definitions, like we've already seen, but it includes other information too. There are types and tables that let you define more complex data structures, reference other functions in your WASM module. Memories define sequences of blocks of memory that you want to pre-allocate. Globals define global variables. Exports define the public interface that your WASM module will expose to outside users. And there are imports that let you say, these are external modules that this WASM module expects to exist. And lastly, there's a space for you to define data and code that will execute when the module is instantiated. The one thing you might notice that we have not spoken about, any discussion of text strings. That's because WASM does not natively support strings. A string in WASM is handled the same way your CPU handles it. It only knows about integers and floats. So to create a string, you allocate a block of memory. You use an integer as a pointer to the position of that memory in the overall memory block. You then use whatever contents is at that memory block to be a list of integers and assign some sort of significance to those integers, be it ASCII or UTF-8 encoded Unicode code points. When I say WASM exposes primitives, that's what I mean, primitives. Remember, this is an assembly language. But just as very few people write raw assembly code anymore, very few people really need to write raw WASM. A much easier approach is to use a compiler for a language that can target WASM. The most notable of these is Emscripten. Emscripten is a backend to the Clang C compiler. If you've got a language that Clang can compile, like C and many others, Emscripten can turn that code into a WASM binary. So let's define a simple C function to do some addition. We use an Emscripten compiler directive to mark the function as keep alive, which is Emscripten's notation for I want this module or this method to be exported. We use the Emscripten C compiler, EMCC, to compile example.c into example.js. Now note that we're not compiling to example.wasm directly. Using C means that there is some overhead. Using a language abstraction means there is some overhead of using that abstraction. There are a bunch of C-related infrastructure that needs to exist for the C code to work. Example.js contains all that bootstrapping code. We also need to tell EMCC the name of the module that we want it to have as we export it, and we tell it to export the CWrap runtime method, which I'll come to in a moment. If our WASM module contained an entry point, so if it had a main method in the C code, we could just include the example.js file in our HTML, and that code would execute as soon as that JavaScript file was loaded. But if we want to use methods in that module, we need to hook into the lifecycle of that module. So in our HTML, we pre-declare an example object, and we define a method to run when the WASM runtime has been initialized. In that method, we define a wrapper for our C method using example.CWrap, which essentially maps the JavaScript types onto the arguments that are going to exist in our C method as exposed to the JavaScript runtime. We then include the example script, which augments the rest of the example object with all the other WebAssembly pieces. Now, for this simple example, there is a lot of overhead. It's a lot more complicated, there's a lot more overhead. This example produces about 100 kilobytes of bootstrapping support code and about 21 kilobytes of WASM binary. However, a lot of that overhead is included just in case. By default, C compilers tend to optimize for compilation speed rather than output size. So when you are ready to go into production, you can tell the compiler to go into optimized mode and strip out everything that isn't needed. And that can dramatically reduce your payload size. That optimization can be done at various levels, which takes a little bit longer to compile the more optimization you do. At optimization level 3, the output of that same C file is about 19 kilobytes of minimized JavaScript and 165 bytes of WASM, which is a lot closer to our original handcrafted 41-byte WAT file. There is still some overhead though, but remember, you do get benefits from that overhead, like for example, not having to write assembly code by hand. Strings are handled almost completely transparently. You can declare a C function as a string. We're taking a string argument, a character pointer, as an argument. It returns a C string, again, a character pointer. On the JavaScript side, we wrap that function as being something that accepts and returns strings, and you can invoke that function with JavaScript strings. Emscripten also makes it easy to interact with JavaScript. Simple scripts can be invoked directly with Emscripten run script, which you can see in our myfunc function call at the bottom there. First call, just call an alert, stored as a string. But here's another example. You can also embed JavaScript code in your C code. So Emscripten provides an EM.js directive, which lets you define a prototype for a JavaScript method, define the JavaScript in your C file, and when you compile it, you can just call that function as if it was C, but it will run as JavaScript. So in this case, we've got two different ways of showing an alert, and the JS add is also doing an addition. The addition is being done in JavaScript. It's being wrapped in C, being invoked over WASM from JavaScript in your original source file. Standing in a hammock. You also get access to a bunch of other tools and APIs that are part of the Emscripten toolchain. Emscripten provides bindings to HTML5 events, so you can write native implementations of keyboard, mouse, scroll handlers. You get access to a file system API. You are still sandboxed. You can't read files on your user's file system, but you do get a virtual file system that you can feed binary blobs of data and access them as if they were C files. You can use the browser's fetch API to access network resources, and you can access all sorts of hardware-optimized APIs like WebGL and WebVR. Now, Emscripten was the first player in this compiled language space, but it isn't the only player anymore. For example, the Rust compiler can compile directly to WASM. The Rust project has really good docs and tutorials about how to write and deploy logic for your web app in Rust if you want to go down that path. Okay, so that's how you generate WASM code, but why is WASM of interest to us as Python and Django users? Well, there are two primary use cases for WASM in production right now. The first is deploying a full application that already exists and is written in C. For example, if you go to quakejs.com, you will find a full port of Quake 3, compiled and running in your browser. It takes about a minute or two to download, but once it's there, it's a full 3D first-person shooter running in your browser. Why does it work? Well, Quake is written in C. It uses OpenGL and it uses keyboard inputs. Those features map really well onto the capabilities of WASM as a mechanism of deploying an application that has already been written. Qt is a widget framework. They are working on WebAssembly support as well. So if you have a Qt app, you can compile that app and deliver it over the web, and you'll get something that looks like your Qt app running inside a browser. Now, I won't say it's trivial to do this, but the Emscripten build toolchain maps really well onto the autoconf toolchain. So if you have a C project with a configure script, which a lot of C projects out there do, it's not that difficult to get it compiled and running in the browser for suitable definitions of not that complicated. Use case 2 is an optimization use case to identify hot loops or critical business capabilities and replace them with WASM implementations. For example, Google has published a demonstrator app called Squoosh. Squoosh is an app for doing image manipulation, for exploring the before and after effects of various forms of image compression, resizing, and resampling algorithms. The actual app itself is a Node app that delivers the basic app content and UI and buttons you can click on and user interface elements. But under the hood, it uses WASM to do all the image processing. Almost all of the image codec libraries out there are written in C or have a C implementation available for them. So instead of trying to re-implement libjpeg in JavaScript, you can use WASM to compile libjpeg as WASM and then invoke it as a C function over the Emscripten interface. If you've got a C library that you need to use client-side, you now can. Or if you are writing a web app that has a hot loop, that has something that is very, very CPU intensive and isn't performing well in JavaScript, you can go and take that method, rewrite it in C or Rust, compile it as WASM, deliver that as a payload, and invoke that hot loop as a function that should hopefully run natively and run fast. If you just want to quickly play around with WASM, the best tool that I can recommend at the moment is WebAssembly.studio. That is a URL, not a product name. If you stick that into your browser, you will get a simple WASM development environment. It looks very much like an IDE. And you can play around with that without having to download the rest of the tool chains and everything. You can write the code, press compile, and it will run. If you like what you see there, then by all means go and download the WebAssembly binary toolkit or Emscripten, Rust's WASM tooling. The tutorials are actually not too bad for most of those tools. Okay, so those are the visible use cases right now, but what does the future hold? How do we make use of Python in the WASM world? Well, again, think back to the start of this talk. I spoke about the path of getting code to run from assembly language to compiled language to interpreted language. And then I described a similar path for WASM, defining an assembly language and compilers that target that assembly language. There is one more step we can take. We can write language interpreters that can be deployed as WASM. Now, I can't say that this is ready for prime time, but there are a couple of projects that are exploring this space. The most notable is probably Pyodide from Mozilla. Pyodide is literally the CPython source code compiled with Emscripten. They've also gone to the trouble of compiling NumPy and SciPy and Matplotlib and a couple other key parts of the Python ecosystem that have C extension modules. If you take the WASM binary produced by Emscripten, compiling CPython, and hook it up to some input elements in a web page, you get Python in the browser. You get a full Python shell in the browser. And the Pyodide demo is effectively a 100% client-side Python environment comparable to a Jupyter notebook session. So instead, like Jupyter is normally a client-side talking to a kernel in the back end, there's no kernel. It's just a web page, a single web page compiling and running your Python code. It is a full Python parser, compiler, and runtime. The downside is that it is big. The WASM file for PyDide is for just CPython is around 3 megabytes. If you want the rest of the CPython standard library and all the other bits and pieces, it gets bigger and bigger. I think it's about 12 megabytes for PyDide. And that's before you've given it any Python code to run. So if CPython is too big, maybe we just need a smaller Python. What about MicroPython? It's written in C. Can we compile that? Well, yes, you can, and it's been done, and it's on NPM. You can install via NPM a JavaScript package providing the MicroPython virtual machine. And it is, yes, smaller than PyDide. The official distribution is just shy of 1 megabyte. These projects are still experimental. They are very interesting developments. But they both take a very similar approach, exposing a full Python REPL, read, eval, print loop, into the browser. My own experimentation in this space has been somewhat different. Batavia is a mechanism that provides Python in the browser by just implementing the CPython virtual machine. If you transmit CPython bytecode on the wire, you don't need a compiler and a parser in the browser. You just need the bytecode machine. Batavia currently does that by implementing CPython bytecode virtual machines, CPython bytecode virtual machine in pure JavaScript. But WASM might provide an alternative here. If you were to take the CPython sources or the MicroPython sources, strip out the parser and the compiler, you will end up with a much smaller Python interpreter, but one that is entirely capable of running CPython bytecode or MicroPython bytecode. It would actually support the C module extension API as well if you were compiling the CPython version. Compile that with some smart tree shaking, and entirely client-side Python starts to look plausible. And that C module capability is itself a point of interest. One of the major reasons that people write C modules for Python is for performance reasons. Take a hot loop in your Python code, write it in C, but using a C module means your Python code can no longer work cross-platform, or at least not without recompilation. But if you compile your C module into WASM, you get a cross-platform binary. All you need then is the ability to invoke that cross-platform binary from your Python code, which is what a Python module called WASM does. WASM is part of a larger project that's attempting to make it cross-platform binaries as a distribution platform in themselves, also well worth looking at. So, wrapping up. In the mid-90s, Java was the hotness because it was going to deliver write once, run everywhere code. It was able to run everywhere because it specified a bytecode format and provide a cross-platform virtual machine. But it strongly coupled that experience, that programming experience, to a new programming language called Java. And the whole world got really enthusiastic about Java, and Java isn't going anywhere, but it also hasn't taken over the entire world. Other programming languages still exist. It wasn't possible to displace the entire ecosystem. JavaScript was invented at about the same time, and it's called JavaScript because of the hype around Java. It has nothing to do with Java, but it needed to be called something Java because of that marketing hype, because it was going to be as cross-platform and as important as Java was in the mid-90s. It essentially was there to be capitalizing on that marketing buzz. JavaScript didn't have a standardized bytecode format or provide a virtual machine to make it cross-platform. It only worked in the browser. But over time, the importance of the web as a platform has meant that people have tried to bring JavaScript everywhere. They've tried to reinvent the universe using only JavaScript, making exactly the same mistake that Java made, focusing on the language, not the runtime. The great irony here is that the promise that Java originally made, write once, run everywhere, that promise may end up being delivered by JavaScript, a language that borrowed the Java name for purely marketing purposes. But even then, we're going to get the capability by ignoring the language. JavaScript has the potential to actually be a universal computing platform, not because of JavaScript the language, but because of the importance of the web as a platform and all of the effort that has been put into optimizing JavaScript runtimes as a result. Almost by accident, we have ended up with WASM, a mechanism for describing cross-platform native executables. And that ultimately is better for everyone because it abandons the idea that there is one programming language to rule them all. Lets every language find its own niche and lets other languages, including Python, coexist and cooperate with that ecosystem. There is a lot of work that still needs to be done before we can speak about having an experience as a web developer that doesn't involve JavaScript at all, or at least only involves JavaScript as an execution platform for our Python or whatever other language you want. I would like to be able to spend a whole lot more time working on this stuff, on Batavia, other aspects of the Python ecosystem. So by way of a quick plug, if you'd like to support my work, you can join the Beware project as a financial member, or if you prefer, you can back me on GitHub sponsors. I am here for the rest of PyCon through to the end of the sprints. If any of this stuff interests you, please come and have a chat. I'd be delighted to chat about any of it. Thank you very much. I think we're at time. No, see ya.